Welcome to the demo video. Here, I'll show you how to use the tools we've built that I've discussed in my talk. They are linked down below. So here, I'll demo the tools we've developed with the use of machine learning so that you can see how we use them and how easy they are to use. And then I'll show you a little bit about the model that we've developed to disentangle electronic and lattice degrees of freedom in phase transitions. Through a combination of human and NLP searches, we've built the first database dedicated to thermally driven MIT compounds, as well as related materials. Here's a demo of how this works. So, here's our database demo. Next is a demo of our online classifier on Binder. This is just a classifier that's in our paper, however, in a Binder format that works in your browser and doesn't require you to install anything. All you need to do is upload a structure file in a CIF format, and you will get a featureization of it, so things like the unscreened Hubbard U estimate and so on, as well as probabilities that the material is a metal, insulator, or metal insulator transition compound. Now I'll discuss how to disentangle the role of the electronic and lattice degrees of freedom in a phase transition, specifically in this case for MIT materials. Now let's take a look at the rare earth nickelates, which show a metal insulator transition as a function of temperature. Going back to the insulating state of an MIT material, in this case a rare earth nickelate with a breathing distortion, we see that it has an electronic degree of freedom and a lattice degree of freedom, namely the electronic disproportionation, and a structural one, which is basically that the octahedra are not the same in size. So provided we know the structure and there is some appropriate electronic degree of freedom, we can write a disproportionation energy of this form. This has a structural term that is quadratic in Q, which is in this case a displacement of the oxygen, so the red atoms. An electron-lattice coupling, which most often is linear and couples the structural and the electronic degrees of freedom. And an energy as a function of the electronic disproportionation, which to some extent we can think of it as the electronic disproportionation energy or the total energy in the absence of any structural disproportionation. So once we have a lattice stiffness K, an electron lattice coupling G, as well as a electronic disproportionation delta N as a function of Q, we can then build an electronic and a total energy functional that allows us to clearly disentangle the roles of the electron and lattice degrees of freedom in the transition. In this case, for metal insulator transition compounds, This is the transition to an insulating, symmetry-broken state. We've applied this methodology to the metal-insulator transition compounds described by the formula RNiO3, where R is a rare earth, their heterostructures, and calcium-2 ruthenium oxygen-4, and figured out that one of the main drivers of the transition to an insulating state at low temperature in both of these materials, as well as in their heterostructures and thin films, is the electron-lattice coupling. For more detail, please see our paper. You can also see how you can get additional insight without performing additional calculations in materials such as strained thin films of calcium ruthenium 4. Thank you.